If you're watching this video, you've probably seen a few Stirling engines. My personal favorites are two I saw on YouTube. This one for its playful creativity and this one for its elegant simplicity. This one is actually being run in reverse as a heat pump or refrigerator. Why is it though that Stirling engines are common in toys but rare in industrial applications? And could that change in the future? Maybe physics can give us some clues. In this video, I'll try to explain the principles behind a Stirling engine, as well as its imaginary relative, Carnot's engine. And yes, we will prove Carnot's theorem, but not with lots of symbols. We'll try to do it with lots of animations. Let's start with this video by M. Lobjinski with two pistons driven by a motor. Viewing with an infrared camera, one sees that the cylinder on the left cools and the cylinder on the right warms. What breaks the symmetry? The rotation of the motor, of course. The left cylinder is a quarter cycle ahead. What does that do? Well, let's mentally change the setup. And then we can see the gas expands on the left and gets compressed on the right. Expands on the left and gets compressed on the right. And that's how the left cylinder gets colder and the right cylinder gets hotter. Now let's imagine that once we have established a temperature difference, we turn off the motor. Now the gas can expand on the hot side, producing force to compress the gas on the cold side. Expand on the right, compress on the left. This will tend to equalize the temperature difference, and it corresponds to the wheel being turned in the opposite direction. In a Stirling engine, all the power comes from the expansion of air. There's no explosive combustion, and there's no water boiling to steam with a huge increase in volume. That's safer, but it's also less power for a given volume and weight. So if you're designing a drone, you probably wouldn't put a Stirling engine in it. But there are other situations where Stirling engines win, and the clue to why is their reversibility. Now, even when we've simplified a Stirling engine with animations, there's a lot going on. Let's simplify further to an abstract machine called Carnot's engine. It isn't quite what Carnot described 200 years ago, but rather a reformulation which became standard later. Carnot's engine has a gas in a cylinder with a piston, and outside there's a hot heat source and a cold heat sink, which you can connect and disconnect, and both of these can give or take large amounts of heat while remaining at the same temperature. Let's slow down this frantic engine and divide each cycle into 4 stages. In the first stage, you connect the hot source and gradually reduce the pressure on the piston to let the gas take in heat and expand at constant temperature. Then you thermally isolate the cylinder and further gradually reduce the pressure to let the gas expand and cool to the temperature of the cold sink. After that, you connect the cold heat sink and gradually increase the pressure so that the gas gets compressed and gives heat to the sink, staying at constant temperature. In the last stage of the cycle, you thermally insulate again and compress the gas so that it heats up to the temperature of the hot source. So constant temperature expanding with heat from the source, then insulated expansion with cooling, followed by constant temperature contraction with heat to the sink, and finally insulated compression with heating. Now things start to get interesting. During the first half of the cycle, the gas is providing work through the piston. During the second half, you have to do work through the piston to compress the gas. So isn't the output work cancelled by the input work? Not quite. To see why, let's consider 2 of Carnot's engines half a cycle apart. The insulated expansion and compression stages are equal and opposite in temperature and volume change. But the constant temperature expansion and compression are not equal and opposite. The expansion stage is hotter and provides more work than is needed for the compression stage, giving some net output work. All heat engines work by taking heat from a source, converting some of it to work, and passing the rest to the sink. The distinctive feature of Carnot's engine is that every detail is reversible, and you can run the whole cycle backwards. If you reverse the cycle, the expansion stage is cooler than the compression stage, so you do more work on the gas than the gas does in return, and you take heat from the cold sink and give heat to the hot source. It's a refrigerator or heat pump. We can think of a Stirling engine as a practical compromise to Carnot's engine. Connecting and disconnecting the heat source and heat sink would be very difficult. Instead, a Stirling engine moves the gas around between a hot compartment in contact with the source and a cold compartment in contact with the sink. We've seen two compartments done with two pistons earlier, but division into two compartments can also be done with a partition that's mostly insulating but slightly porous. The displacer is not in phase with the piston. It differs by a quarter cycle. Integza has a bunch of marbles for the displacer and uses the tilt of the cylinder to move them at the right point of the cycle. Like Carnot's cycle, the Stirling cycle can be run backwards, but there's a difference. When Carnot's engine runs backwards, each stage is exactly the reverse of a forward running stage. In a Stirling engine, there's always some heat leaking from hot to cold, whether you're running forwards or backwards. That is to say, Carnot's imaginary engine is thermodynamically reversible because it can undo all its side effects on the environment. Stirling's real engine cannot undo all its side effects, which makes it operationally reversible but not thermodynamically reversible. What about an engine and a refrigerator together? You could have one of Carnot's engines running forwards, taking heat from a source, passing some to the sink, and use its network to drive another of Carnot's engines running backwards. We could have this nice oscillating pair of pistons with no net effect on the environment. Now suppose someone comes along with an engine that can produce the same network with less heat from the source. That would be amazing indeed. You would be taking less heat from the source than you put in, the work would be equal and opposite, and as a result you would take more heat from the sink than you put in. A refrigerator with no net input work, otherwise known as a perpetual motion engine of the second kind. No, we don't think anyone could make that. In fact, we're so sure nature wouldn't allow it that we call it the second law of thermodynamics. Let's follow our reasoning a little further. We've just seen that for a given hot source and cold sink, the highest output work per input heat that you can keep doing in a cycle is for a thermodynamically reversible engine. We had Carnot's engine in mind, but any thermodynamically reversible engine would provide the same. So the maximum output work to input heat ratio is really a property of the heat source and heat sink. Now, there are only two properties of the source and sink that we actually used. One is that they are large reservoirs of heat. They can give or take large amounts of heat. But this property is always the same, so it can't be relevant. The other property we used is that the source is hotter than the sink, and this has to be the relevant property. It's the temperatures of the source and sink that set the performance of a reversible engine. This fact is called Carnot's theorem, and the argument we just went through is a proof, even though we didn't write down anything. Carnot's theorem doesn't specify a temperature scale, but as a corollary, it lets you define a temperature scale. Thermodynamic temperature is actually defined such that the sink to source temperature ratio equals the output heat to input heat ratio. We're talking about thermodynamically reversible engines, of course. Since the difference of output and input heat is output work, we have 1 minus the temperature ratio equals the ratio of output work to input heat. That is to say, the greater the temperature contrast, the more output work you can get for the same amount of heat. For a refrigerator or heat pump, input and output get swapped, and the greater the temperature contrast, the more input work you need to pump the same amount of heat. Since Stirling engines are operationally reversible, even if not thermodynamically reversible, we might guess they're more efficient, that is, they can get better heat to work conversion. Is that true in practice? I didn't find any conclusive documentation, but it seems at least plausible. Here's a company specializing in turning waste heat from combustion into electricity, and Stirling engines are what they use. And here's a heat pump under development that also uses a form of Stirling. I don't have any engines, reversible or otherwise, to show on camera, so let me end by sharing an insight which actually goes back to Carnot. Using heat to turn a wheel is sort of like using falling water to turn a wheel. For a water wheel, what matters is not only the amount of water, but the height through which the water falls. If instead you use heat to turn a wheel, the role of height is taken by temperature.